Hello, everybody. This is me again, Juan Miguel Morales, and I'm going to give the last talk of this session. The title of my talk is Homothetic Inverse Optimization Approach to Forecast the Price Response of a Pool of Buildings. This is a joint work with my colleagues Ricardo Fernandez Blanco and Salvador Pineda Morente, which has received funding from the European Research Council. Okay, let us put ourselves into context. Suppose we have a cluster or pool of buildings and houses within a neighborhood or community that are equipped with thermostatically controlled loads. Furthermore, suppose that the owners of these buildings want to make some profit out of the building's thermal capacity. How? By shifting or reducing their load in response to a 24-hour electricity price vector that is sent to the buildings one day in advance. So the idea is that the thermal consumption of these buildings is controlled in such a way that the electricity bill is minimized while ensuring occupants' comfort. Our goal then is to model and forecast the aggregate price response, that is, the aggregate thermal power consumption of the ensemble of buildings. We are facing three main challenges here. First of all, we want to do this prediction one day in advance for the 24 hours of the following day. Furthermore, we want to do it well, and for that purpose, we will need to capture both the thermal dynamics of the pool of buildings and the user's reluctance to experiencing discomfort. So let's see how we are going to do this. This slide introduces the key ingredients of our approach. Throughout the presentation, we are going to talk about a building prototype, which is going to represent the average behavior of the pool of buildings. We will use the superscript P to represent the operational variables that refer to this prototype building. We will consider that the feasible operational region of the actual ensemble of buildings can be described well enough, at least, as an homothet of the feasible operational region of that building prototype. This homothetic transformation is going to be characterized by two parameters, namely the dilation factor beta and the translation vector tau. Okay, the variables and parameters corresponding to the aggregate building model will be identified with the superscript A. Our forecast model will also make use of a piecewise linear utility function with marginal utilities M. These marginal utilities drive the maximization of the building's users' welfare and the minimization of their discomfort. Finally, we will use inverse optimization to infer or statistically estimate parameters beta, tau, and m, which characterize our forecasting model, which is in turn formulated as an optimization problem. That's why we need to use inverse optimization for the statistical inference. This is the model we use to capture the thermal dynamics of the prototype building. It is essentially a first-order discrete dynamic model where in blue, we have indicated the parameters or data that we know, while in black, we have the operational variables that are to be controlled or kept within certain limits. For example, this variable P represents the cooling power because we are considering only here cooling mode. This cooling power must be lower than the rated power capacity, which is a blue parameter, okay, it's data. Then besides, theta here stands for the state variable, which is the indoor temperature that must be kept within the comfort bounds, upper and lower. The theta amp represents the outside temperature, and parameters A1 and A2, okay, are characteristic parameters that depend on the building thermal properties and the discretization time step. This is exactly the same model as before, but in a matrix form, okay? Here in 5, sorry, we have the equations. The equations are given for all the hours of the day, while here we have collapsed them using matrices and vectors. So here comes the core idea of our approach. We assume that the aggregate cooling power, PA, can be obtained as a homothetic transformation of the cooling power of the building prototype. So 3A and 3B are just constitute the model of the aggregation of buildings that results from this transformation. In pink, very importantly, we have highlighted the parameters beta and tau that characterize the homothetic transformation, and that we will need to estimate statistically using inverse optimization, as I will explain later. So we are now ready to introduce our forecasting model. 4B, 4C, and 4D, here, here, and here, okay, are the homothetically transformed thermal equations we have just seen. In the objective function, we have the maximization of the pool utility by way of the vector or marginal utilities, and the minimization of the discomfort cost. So how does this model work? Given the 24-hour vector of prices, lambda d, which is a blue parameter because it's given, okay, we solve this utility maximization problem that capture the pool thermodynamics by means of 4B, 4C, and 4D, and to compute the forecasted aggregate cooling power. As I said before, we consider a piecewise linear utility function, which renders a stepwise marginal utility function as the one that I'm representing here as an example in this figure. This one consists of 3 steps. The aggregate cooling power is given as the sum of the contributions from each of these steps, okay, or block. Just mention also that we make the vector of marginal utilities, which in this example is characterized by 3 values, M1, M2, and M3, as an affine function of some covariate information that I will explain later what this is exactly in our numerical experiments, okay, but it's given info as well. So the question now is, how do we estimate the characteristic parameters M, beta, and tau? Okay, these are the parameters of an optimization problem, our forecasting model. So we use inverse optimization, which translates into solving the following bilevel program. The idea is that given observations about the aggregate consumption of the pool of buildings, the associated vector of electricity prices, and the covariate information, the upper level computes beta, tau, and the vector of marginal utilities, such that the cooling power delivered by our forecasting model, that is the lower level problem, matches as much as possible the observed one. This here is the vector of the observed aggregate power of the pool of buildings in DAD. Okay, we do this on a training set. The upper level problem also includes constraint 5D, constraint 5C, this one, to guarantee that the piecewise linear utility function is monotonically increasing. The upper level variables beta, tau, and m, which enter our forecasting model, the lower level problem, okay? Then we have the upper level that seeks to minimize the absolute error, the mean absolute error on the aggregate power consumption of the pool of buildings. Okay, just to mention that the way we solve this bilevel problem is by means of a solution approach consisting in regularization and initialization. Further details on the solution approach that we use can be found in the preprint of the article that I mentioned here as a footnote. This is just a graphical illustration of what our bilevel programming problem does. We estimate, we have a series of observations of the aggregate power consumption of the pool of buildings. Each data point is characterized by a vector of electricity price, an observed power consumption of the pool, and some covariate information. The idea is that we compute tau and beta so that these observations are feasible. And this feasible region is determined by an homothetic transformation of the feasible region of the building prototype, which is represented here with this polygon. Okay, but furthermore, we also compute a vector of marginal utility so that these observations are not only feasible, but also optimal. Optimal for our forecasting model, which is an optimization problem. Okay, next we present some results from numerical experiments. In particular, we have tested our approach on a synthetic data set that has been obtained assuming that the thermal power consumption of each building in the pool is controlled by means of the optimization problem that I represented here, optimization problem 6. This optimization problem seeks to minimize, okay, the electricity bill of each building plus some discomfort cost. These costs are given by a penalty that multiply the deviations of the indoor temperature, okay, with respect to the comfort bounds. Equations 6b and 6c model the thermodynamics of the building, as we have seen before, and the buildings in the pool are different according to a heterogeneity factor H bar. This H bar controls how different the buildings in the pool are. In particular, the parameters of the building are sampled from a uniform distribution, like this one, whose mean is equal to the values of the parameters for the prototype building. We simulate this model, model 6, for 100 buildings and 78 days. We use 35 days for training, 35 days for validation, and the last 7 days for testing. We have created two synthetic data sets, each with a different heterogeneity factor, naming H bar equal to 0.1 and H bar equal to 0.75. Observe that the highly heterogeneous pool features lower peak demand, lower mean, and no hour without consumption. We employ as covariates the outside temperature for the current hours and the previous and posterior 2 hours. We use CONOP to solve the regularized nonlinear problem that results from the bilevel inverse optimization approach. Here I present the methodologies that we have compared. HIO is our homothetic inverse optimization approach. NTD is the inverse optimization approach proposed inside Gallego and Morales, where they do not explicitly account for the thermodynamics of the pool of building. ARIMAX is a classical autoregressive integrated moving average model with exogenous variables. And then we have the naive model, which is basically a persistence model such that the forecast in day D is equal to the observed values in the previous one, in day D-1. Okay, in this table, we compile all the results related to these numerical experiments. We have used the mean absolute error computed over the test sets to assess and compare the different methods. We test then, as I said, on the two synthetic data sets that I mentioned before, each corresponding to a different level of the pool heterogeneity, and for two different numbers of marginal utility blocks, specifically 1 and 6. We highlight in pink the best outcome, that is the lowest error. First message that we have to take away: it is apparent that forecasting the aggregate demand of a highly heterogeneous pool of buildings is way much easier than doing it for a low heterogeneous pool of buildings. Just see the order of magnitude of the error metrics. In fact, our approach systematically outperforms the other methods in all cases. Actually, the ARIMAX model is always competitive in the highly heterogeneous case. Besides, by comparing HIO and NTD, we can see that explicitly accounting for building thermodynamics is significantly very advantageous. Finally, the number of marginal utility blocks has a substantial impact in the highly heterogeneous case, for which there is a more clear and smooth dependence of the aggregate cooling power on the price. In fact, we can notice in this figure that increasing the number of marginal utility blocks served us to smooth out the price response of the pool. The black line here represents the actual observation of the consumption of the pool of buildings for a random day. And we can see that by increasing the number of blocks, that is by going from the red curve to the green curve, what we have done is to smooth out the forecast of the aggregate cooling power of the pool of buildings. To conclude, we have presented a novel technique to forecast day ahead the aggregate demand of a cluster of buildings. This technique has been built on a homothetic inverse optimization approach that is formulated and solved using bilevel programming. Our approach explicitly accounts for the built-in thermodynamics while drastically reducing the number of parameters to be estimated thanks to the homothetic. Furthermore, our forecasting and model represents a representative built-in operational model thanks to the inverse optimization approach, which makes it very interpretable and versatile. On top of that, it outperforms other techniques available in the technical literature. So that's all. Thank you very much for your attention. Further information, as I said before, can be found on the preprint of the article, which is available through arXiv. I'm willing now to take some questions. Thank you.